All right, welcome back. Let's settle in quickly. And I think we will try to go maybe 10 minutes extra in this session until 5:40 or so. And I would also say maybe we can keep 3 or 4 questions per question that Robert is going to ask. And then maybe we can ask more questions at the end so that we finish the story. And Robert will be here tomorrow as well, so we can all bother him. Please, Robert, take it away.
Yeah, so sorry for the technical difficulty that we run into. Hopefully it will be smooth from now on. But yeah, so after seeing this, I just hope people have some time to think a bit more about quantum certification, in particular this task about certifying QIP state. Kind of not very lucky, kind of unlucky that it seems like it's quite hard to even certify what are the unknown state is the QIP state of some Hamiltonian, but that's just the way it is. And now I would like to move on to talk a bit more of the other two questions. That is, what about this task? I will try to create some state in the lab, and I wanted to certify if I have succeeded or not. And also this one, let's say I have some AI model that tried to learn a representation of the unknown state role in the lab. How can we make sure that the AI model is not hallucinating and is correct? So both of these tasks can be more broadly kind of talked about under this one, which is called state certification. And it has been it's a very old task that the quantum community have studied for many decades. And the task is very simple. We have some desired unqubit state psi, which is our target state. One could also think of this state psi as being the state that was learned by some AI model. And then that's the state that's in our mind. But then in the real world, there's another state, a density matrix rho that's created in the lab. And state certification is the task of checking if the state in the real world is close to psi or not. So here one can think of the closeness to be measured, say, in terms of fidelity. So how can we solve this task? So there's an approach 0, which is kind of a very direct one, just by directly measuring it. So suppose that the target state psi is U, some quantum circuit, applied to the all-0 state. Then one way to perform state certification is we just implement U inverse, apply onto the lab state rho, and then we just measure all the qubit. If we see that everything becomes 0, or if we count how many times everything is 0, then we will be able to get an estimate for the true fidelity, and that way we can do certification. Yeah.
1 second question. When you mean we know the psi, do you mean we have like a classical description of psi?
Yeah, so here you can think of we have some classical description. Maybe it's a tensor network. Maybe it's just some representation, some classical representation. Maybe it's a neural network, some arbitrary classical representation for psi.
Thank you so much.
So we have full knowledge of it. Okay. So here's an approach 0. The reason I said it's approach 0 is because even though it does solve the task theoretically, it's not a very good solution. So what are the challenges that arises in this approach? So if we can assume that one can implement U dagger perfectly, then in a way one should be able to assume that U can be implemented perfectly as well. And if that's the case, then in this world one can just create the density matrix rho to be equal to psi perfectly. And hence in this case we probably don't need to do any certification. So this approach 0, while it kind of solved the task theoretically, in practice, no one really uses it to do state certification. Let's say an experimentalist try to prepare some state, but it prepares some noisy state role. And to certify or to falsify that it has done it, no one really runs this approach. So now here's some simple questions. So for the following states, how can we efficiently certify it? So we have some state rho in the lab, And then hopefully we wanted to create it either to be a simple product state, O plus state, or maybe it's this GSG state, or it's the Toriko ground state, let's say encoding logical state 0. How can we efficiently certify whether rho is equal to one of these target state or not by utilizing no entangling gate? So we cannot just run the preparation circuit or the state prep circuit in reverse and just measure it. We wanted to do it without any 2-qubit gate. So maybe just 1 minute so one can think a bit about what are some ways for us to achieve this. And feel free to also ask a few questions while you're thinking about it.
When you say do it without 2-qubit gates, you mean only single qubit gates, or can we have larger gates?
Yes, that's a good question. Yes, no entangling gates. So the capability is you can perform arbitrary single qubit gates and then perform standard computational basis measurement, but you cannot entangle things. So you cannot run any non-trivial circuits on top.
I mean, I'm not sure if I'm missing something, but over here. But for the first one, can't we just measure a few qubits in the X spaces or apply a
Yeah. For that one, that's a trivial one. Just measure in the plus minus spaces and then check that you get all plus. That was solve it.
Cool.
Right. These are all stabilizer states, so just randomly sample a constant number of stabilizers.
Yes. So for these simple states, or more generally any stabilizer states, one can just measure the stabilizers, maybe just sample a basis or randomly sample some of them, polynomial number of them or a linear number of them, and just measure them. And then if you check that all the stabilizers are satisfied, then you know that this is good. So indeed, so these are pretty simple states, and there are ways to do it. And however, if one wants to apply this for any state psi, then it's not as clear how one could do so. But let's just take a step back and think a bit about what are some general scheme that one can utilize that's not approach 0, where we just directly measure the state. If you wanted to do state certification, are there other ways of doing it? So one approach that can be directly applied is by utilizing, say, random Clifford or other random 3 design circuits. So what one could do is one could sample some random Clifford circuit, apply it to the quantum state, and perform standard basis measurement. And then from the measurement data, along with the knowledge of these random circuit, one can create classical shadow representation. And from there, one would be able to predict all kinds of observables that have bounded Frobenius norm, which in this case, psi would be the observable that we wanted to target. And hence, from there, from these measurement data, we will be able to estimate fidelity using a small number of samples. So this is another approach that one could do in order to do state certification that experimentalists are doing right now. So the advantage of this compared to approach 0 is that one only needs to apply random circuits that form 3 design. And actually only approximate 3 design is enough. So naively, one can implement some linear depth Clifford circuit, but that could be a little bit too deep. However, luckily, recently we have seen that actually forming approximate 3 design, even on 1D circuit, can be done in just log depths. There's also going to be a plenary talk about this in more detail in the coming week. And hence, for this approach, all one needs to do is to just sample some shallow 1D circuit to scramble it. Instead of a deep random Clifford circuit, just a shallow one is sufficient. And then one can run this approach. However, the challenge is that even doing so could still be quite costly and challenging in actual experimental setting, because implementing entangling gates always generate noise, and hence this is also not ideal. Another challenge of this approach is that the runtime can be extremely high. So in particular, what one needs to do in order to apply this is that one needs to be able to efficiently calculate these numbers. So the overlap between S, which is this single shot classical shadow. In this case, it would just be some, let's say, random stabilizer states with the target state psi. And if we cannot efficiently calculate that, like maybe psi is represented as some tensor network or some neural network representation, and from there, it's not clear how one could efficiently estimate this, then this approach would still fail. But the main problem is that for this approach, even though the circuit is shallow, it still requires relatively large number of entangling gates, and hence it could be challenging in many experimental settings where we can only perform non-entangling gates. So here's another question. How can we certify any state psi using just single qubit measurements? So we don't allow any entangling gate, but for now, let's say we can be non-efficient. How can we do it? So here's the hint just give it away. It's a very simple question. Basically, the goal is to estimate trace of psi rho. And hence, if we just expand it out psi in terms of the stabilizer or the Pauli basis, then one just keep measuring the different Pauli terms and combine them. Of course, it requires exponential number of single qubit measurement. But at least using this way, one will be able to estimate trace of psi rho. And this gives rise to another approach that people often do in practice, which is one just perform some randomized Pauli measurement. So we start with a state rho, and now we just randomly measure different qubits in a different Pauli basis. And from there, we will have enough information that allows us to predict the fidelity, and hence one will be able to perform state certification. So the advantage of this is that it only requires single qubit measurements on state rho. However, the challenge is that in many cases, for most target state, this will require an exponential number of measurements, which is highly inefficient. And especially if the target state psi is highly entangled, then this Pauli basis representation will just look pretty random, and we have to just go through a large number of these Pauli terms. So that's also not an ideal situation to be in. So in practice, what one often do, which initiated from the quantum supremacy experiment, is to perform cross-entropy benchmarking. So hopefully many of you have heard of this, and it's a very common strategy that people often do to do state certification. But let's see if it actually does state certification. So the cross-entropy benchmark is a following method. Basically, we take our state, and then we just measure in the single qubit basis. This will sample a bunch of bit strings. And from the bit strings that was being sampled, we can calculate these XEB score. So the score is just given as that formula. So essentially what this is calculating, or by doing these measurements, what we're calculating is this expectation value of X sample from the diagonal of rho, and then we'll calculate the probability amplitude squared in order to obtain a number. And then after we properly normalize it, that's the XEB score. So here's a very simple question. Suppose that the state rho is approximately given by white noise. So our target set is psi, and let's say the noise that's affecting the system is roughly white noise, meaning that it's just a slightly depolarized channel applied onto psi, and that will create rho. Then is XCB a good certifier? Like by checking the XCB score, are we able to efficiently certify in this case? So that's a question. People can play with it a little bit, and hopefully the answer will become very clear. And let me know if there's any questions so far.
Hi, I had a clarifying question.
Yeah.
In the challenge statement that you wrote a few slides ago, you said for most target states psi, and psi is the state that you have a classical description for. So then how do you define like the class of states which have this? Like how do you go about mathematically defining?
Yeah. So here, let's assume we forget about this constraint that psi must have a classical representation. So just think of the space of entirety. So let's say maybe it's a hard measure, and in that case, we can formally talk about most. Otherwise, yeah. Otherwise, it gets a little bit tricky to talk about it.
Thanks.
But yeah, but hopefully after a little bit of calculation, it wouldn't be hard to see that in this case, XCB is actually a very good way to do certification, because when rho is just applying, like when the noise affecting the experimental lab is completely white noise, or it's approximately white noise, then XCB score will just be approximately the same as the fidelity. And hence, by just looking at the XCB score, we will be able to check, like if the XCB score is close to 1, then we know that the state will be close to, rho will be close to our target state psi. Whereas if it's far away from 1, like it's much more closer to 0, then this would, then rho is far away from, or sorry, and if it's close to 1, then rho is close to psi. But if it's far away from 1, then rho is far away from psi. However, one could also ask the following question. Is XCB actually a good certification algorithm? Does it really do the purpose of certifying a state? Which is, if rho is close to psi, then it should certify it. On the other hand, if rho is far away from psi, it should falsify it. And here's the question. Does there exist some state rho and target state psi such that the XCB score says it's perfect, it's 1, but the fidelity between them is actually very close to 0? So if you know the answer, feel free to just raise your hand and set it.
Yeah, I think the all plus state and the all minus state should have the perfect XCB.
Yes, that's right. There are tons of different examples. So definitely, yeah, because XCB score is only only an object that measures the z basis of things. So it could be that one would have perfect XCB score, and yet the distance is extremely far away. So even though people often use XCB as a tool to perform benchmarking and perform certification, in many cases it's highly limited. Another example is when the state is subject to dephasing noise. So instead of subjecting to depolarizing noise, let's say all the off-diagonal elements is being dephased, then in that case, one would also have an XCB score that's equal to 1, and yet the true fidelity would be very close to 0. So while a lot of people have been using XCB, a lot of experimentalists have been using XCB because its main advantage is that it only requires using single qubit measurement, in particular just z-basis measurement, which is very simple on rho. It doesn't really rigorously address the certification task because the state can be very far away from psi, and yet it still has a perfect XCB score. But what about the following? So can XCB be used to certify most quantum states? So here, think of it as the target state psi is sampled uniformly across the hard measure. And now I just run XCB on state rho. And can it be used to certify most states? Like, does it apply to generic states? So we've seen that this O plus versus O minus, which is might be a bit more fine-tuned. XCB would fail, but what about this?
Sorry, I just had a question in the 2 slides ago,
Yeah.
where you defined XCB.
Yes.
How do we get the top inner product like xi the whole square? How do we?
Yeah, so in XCB calculation, people often assume that there's this model, kind of like a query model, where if you're given some bit string, then you will be able to obtain the probability amplitude associated to that bit string. So I guess you're asking how do we get xi, that?
Yeah, because I guess to know psi, you had to apply the unitary, right? And only the quantum computer is able to do it.
Yeah, so in many cases where cross-entry benchmark work, it would require having some classical representation where this calculation would be easy. Or one would have to take a long time to just compute it. Yes. And the same also holds for the denominator as well. Like that number, one would have to find some way of calculating it, otherwise it wouldn't work. But even assuming that all of these computations can be done efficiently, yes, one can still ask this question. If you know the answer, also feel free to just set it. It shouldn't be too hard.
Okay, just taking a shot here, but is the answer no because any string of plus and minus states or anything that's close to that will have similar XEV score? Is that
The answer is no. Yes.
Yeah, okay. But is that explanation correct or not really?
It could be correct, but I think. But there's a simple answer to this as well.
Okay, thanks.
No problem.
Say your target state and the state that you have prepared, which is rho, happen to have the same amplitude in the computational basis, but have very different phases. So under that kind of condition, XZB score can still be very, very high, but the states are so far apart from each other.
Yeah. So basically, like even if we consider generic target state, as long as the noise has certain form, let's say we have dephasing noise. So the state rho in the lab is just has the same diagonal as psi, then XCB can easily fail. So we can see that even though people trust XCB quite well and have been using it a lot in different experimental setting, there are a lot of downsides to using XCB in practice. Like it couldn't capture certain noise, it doesn't even work for generic state, and so on. So then the next question is the following. So is there any way that we can certify almost any state psi using just a small, say, polynomial number of single qubit measurements? Or can we somehow also show that maybe the answer to this is no? Because intuitively it felt like if we only have single qubit measurements, then we will only be able to see things that are very localized, and we won't be able to see, say, some complicated entanglement inside of a state. So is it possible to actually certify it? Or this is a hard problem similar to certifying Gibbs state?
I'd say at least to circumvent the last problem, we could choose, instead of choosing our bit strings in the Z basis, we choose at random a set of bases of measurements. And we do the same thing, but now we replace the bit strings by like the eigenstates of the basis we chose. And so we do XCB, but in random Pauli basis.
I see. So that definitely fixes the problem, but at the same time, it could be a possibility that that would work, but I guess the question would be, how can we show, or is there a reason to believe that by just choosing a few random bases and running XCB in the random basis, then we will be able to certify almost any state. But that is an interesting protocol to try out.
Sorry, like earlier you just said random basis. Do you mean like one random basis for each qubit? Or just like global random basis?
Yeah. So I guess I guess he probably meant random basis in each qubit. So.
But I couldn't, I mean, maybe there are some clever ways to do it, but I couldn't see a way where if you only know information for each individualized qubits, you can somehow gain information about global entanglement properties.
Right. So you're leaning more towards that. The answer to this should be actually no, I guess.
Maybe, I don't know.
But yeah, that's I would have guessed that. Yeah, I would have also leaned to that.
But then stabilizer states are highly entangled states, and you can certify them. So that's a counterexample to that argument.
That is true. That is true. So local measurements or single qubit measurements can be kind of powerful, as showcased by stabilizer, like certifying stabilizer states. However, in a way, stabilizer states are also very classical. But most states would be quite quantum. So yeah, so I hope people have some way of thinking about this. I'm not going to say the answer right now. I'm just going to continue forward. But I'm going to talk about a measurement protocol. And hopefully, gradually throughout the tutorial, it will become clear what the answer to this question is. So let's consider a very simple looking measurement protocol. It's a single qubit measurement protocol. And it seems kind of weak, but hopefully we'll see that it's more powerful than it seems. So what the measurement protocol do is the following. So first, we will randomly pick a qubit x. And for that qubit, or for everything except for that qubit, we're going to measure them in, say, the z basis. And for qubit x, we're going to measure it in a random xyz basis. And that's the entire protocol. So let's just focus on this very simple looking protocol. It just measures things, most of the qubits in the z basis, and one of the qubit in a random xyz basis. So it definitely only do single qubit measurement. And furthermore, it's very similar to just an all z basis measurement, which you have seen is very weak in capturing information and doing certification. So I hope the measurement protocol is clear. So now here's the question. Suppose we have done multiple rounds of these measurements, and we have a collection of data set consisting of measurement coming from this very simple one. Is the measurement data sufficient to allow us certify the following states? Say either the all zero state. Can we do that? Does it allow us to certify the all plus state? Does it allow us to certify any product state? And does it allow us to certify any phase state? So any state that's a uniform superposition over things, but the phases are just some random or some arbitrary plus minus. So if you have any thoughts, or you think some of it should be easy, but one of it may be hard, feel free to also just state your thinking.
This is very silly clarification, but you only
Yeah.
said to measure once, or is this at
Oh,
multiple?
yeah, you can do it many rounds.
Yeah. So many
Yes.
rounds, and each time you pick a different random qubit.
Yes.
Okay, good.
That's right.
Thanks.
And you know what the random qubit angle
Yes,
is?
we know what the random qubit is, and we also just randomly pick X, Y, Z, and we know all of that.
Yeah, so if you can do many rounds, then you should be able to certify all of them. At least the first set. And
Yes,
I
zero
think,
to the n or plus to the n. That makes sense.
Also,
For example, 0 to the n, I mean, there's going to be a chance where you measure everything in z bases, and from those data, you should be able to check whether it's close to all 0. Plus to the n, the way that works is basically there's a chance that you're going to see, you're going to measure x on that qubit that you selected, and hence from there, you can check whether it always appear plus whenever you do that. Hence, one can use those data to certify 0 to the n or plus to the n. So that is definitely sufficient and also efficient to do. And any product state is kind of similar because randomized XYZ basis measurement allows one to predict single qubit fidelity on any qubit. And hence, from there, one can also certify any product state. But the tricky thing, I think, is the last one. So how would the measurement, is the measurement data sufficient to certify the third family?
For the third one, isn't third one just like a eigenstate of the h to the power of n, like the Hadamard matrix? So that's I was just measuring plus minus basis. That would work.
So if the function f is simple, then yes. But in general, let's say f is just some complicated high degree function, then not necessarily.
Okay, I see. That makes sense. Yeah, I don't know.
And in general, I don't know how people are familiar with it, but by choosing f to be, say, a pseudorandom function, then that could be one could generate pseudorandom state that way. So basically a state that is indistinguishable from any hard random state. So while the third one might look quite simple in some sense, by choosing f to be quite complicated, like a pseudorandom function, then that state can be highly entangled and very complicated.
Isn't the last option a general form of a stabilizer state because you've normalized it as 1 by square root 2 power n?
So if f is a linear function or a quadratic function maybe, when f has more structure, then yes. But in general, it doesn't need to be a stabilizer state. So a stabilizer state wouldn't be able to form pseudorandom state. And by choosing f to be pseudorandom, then the last example would be a pseudorandom state. And hence, it will not be, in general, it would not be a stabilizer state. If it does, then yes, then we can also certify it officially.
Oh, thanks.
So if the answer to the third case is positive, would you be able to construct a distinguisher of a pseudo-random state from random?
Yeah, that's also a good question. In a way, not quite, because the state would be pseudo-random if we don't know f. But here in this case, we do know f, because that's the target state. That's the state in our mind. And the state in the real world is rho. So we know what f is, and we can utilize the knowledge of f in order to do certification. And hence, even though that felt like maybe you could pose a challenge, like maybe the answer should be no, because it might be able to allow us to tell between whether it's pseudorandom or not. Actually, it doesn't, because in the pseudorandom case, we don't know f, and that's part of the hardness. But here, we do know what f is. But yeah, thanks for all the different thoughts. I think that was very helpful. But I don't think right now we have built up enough tool to answer this. But the answer is actually yes. There is a clever way so that one can utilize the measurement data such that it is sufficient to certify all of these cases. And what I would like to do is to provide additional tools that allows us to answer this in the affirmative. So how do we post-process it? Of course, the measurement data given to us, we can do whatever things we want with it. But there's one way that we can think about this measurement data that can be very helpful. So first of all, we can think a bit about what the measurement outcome on the z-basis measurements actually provides us. So if we think of, let's say, an n-qubit state, or think of this n-bit string that comes out of it to be living on this hypercube, then basically the measurement outcome that comes out from the z-basis measurement, it specifies an edge on the hypercube. So the reason I said that, like for example, here it's a 3-bit hypercube. And let's say we have chosen the qubit x, the one that was measured with a random basis, to be the middle qubit. Then let's say we measure the other two, and we saw 0, 0. Then it essentially specifies this edge on this hypercube. So the edge connecting 0, 0, 0 to 0, 1, 0, corresponding to either we fill in the selected qubit, the blue qubit, the qubit x, by either 0 or 1. So in a way, one can visualize the measurement outcome on the z-basis measurement as this. So now after we focus on that, we can then look at, let's say we first measure everything else in the z-basis, or we focus on that part. I mean, the measurement data is already there. Then after doing that measurement, it will cause a collapse of the entire state to the specific measurement bit string that we got, the n-1 bit string that we got, as well as a post-measurement 1 qubit state on qubit x. So the qubit x, the blue one, will now collapse into a state that is proportional to the form that was shown there. So b0 psi times the 0 state plus b1 psi times the 1 state. So in the case of this random phase states, when we do this measurement, it would collapse into, again, just a single qubit phase state, where the corresponding phase in front will depend on what the bit string or what that edge on this hypercube is. So I hope this part is still clear. And then basically what this randomized measurement, we can post-process the randomized measurement on that single qubit using, for example, the classical shadow formalism to essentially create a single shot classical shadow on qubit x. So there it will be a single qubit or like a reconstructed 2 by 2 complex matrix, where in expectation, it will be equal to the post-measurement state, this ideal post-measurement state. But of course, there will be random fluctuation coming from this random choice of Pauli basis, and also the random measurement outcomes that comes out. However, from there, we will be able to predict the fidelity. We can use the measurement data on that single qubit to obtain an unbiased estimator for the fidelity between the actual state on that single qubit and also the ideal 1 qubit state. So this psi b1, b0, b1 just correspond to that edge. It's just some single qubit state that we can compute using the classical representation we have. And now from there, we just utilize classical shadow formalism to predict the fidelity. So that's how we do this post-processing. So of course, there's tons of ways of analyzing the data and doing all kinds of post-processing. Let's say we do this. And now we just average over this real value omega, which is just an unbiased estimator for the fidelity. It's a 1 qubit fidelity to get the average quantity E omega. And let's say that's the whole process. So we do this measurement that we talked about, which we also think a little bit about what is this capable of doing. It seems kind of weak, but then what we do is we analyze the data coming from just one shot measurement this way. And then because we do multiple shots, now we just average over all of these different omega that come from different measurements in order to obtain this expected value, E of omega. And here's the question. So after going through this, after running this procedure, which is a very simple procedure, we just measure everything except for one qubit in the z basis and that single qubit in an xyz basis. And now we go through this post-processing. Hopefully you all have the slides to go through and check what's happening. What is this analytical form of this E omega that we have created? So here the omega is the estimator for the fidelity with this ideal one qubit state. And there's a way to write down a simple analytical form for this. So yeah, feel free to think a bit about it and also ask me any clarification question regarding either the measurement protocol or the post-processing, etc.
So in the measurement protocol, we start by choosing a random qubit x on which to do the random XYZ measurement. But then in the post-processing step, are we fixing like which qubit x on which we're computing this estimator?
Yes. So during the measurement, we are randomly choosing one of them. And here in the post-processing, the data analysis, we're just looking at which one we choose and then running this. So we have the full knowledge of what the measurement we did is, including which qubit is selected, where we perform a randomized measurement, and what are the other qubits where, what are the outcomes on all the other qubits.
Okay.
Just a clarification. This is still for the -1 to the f of x state, right? That we're talking about.
So here you can think of it more generally. It could be the -1 to the f of x state that we're trying to certify, but it could also just be some arbitrary target state psi.
All right.
Yes.
Thank you.
Hey, here on your left.
Oh.
When you average, what you get like the overlap between rho and like some state that looks like psi.
Yes.
Okay.
Yes, but when we average over it, it will be averaging over different choices of x, of the qubit x, as well as different choices of the basis that we measure in, and as well as the different measurement outcome that come from all the rest of the qubits. So we will be averaging over all of that.
Okay.
Yes.
Thanks.
So hopefully there is enough time to just think through this protocol. But essentially here's the analytical form. It still looks a little bit weird, but in a way it is quite simple. The first average just corresponds to which qubit we're choosing. And then there's a second sum that corresponds to all the possibility of the rest of the qubits. So we are going to choose qubit x. Here x corresponds to I. And then for all the rest of the qubits, we're going to measure them and get some bit string which is specified as b not equal to I here. We are going to get that bit string with a probability that is proportional to the trace of this b not equal to I row b not equal to I. And there's going to be also the other part. And that other part corresponds to the ideal one-qubit state. So a way to just write down the density metrics correspond to the ideal post-measurement one-qubit state, psi b0, b1, is given as that form. So we're just taking psi, and note that this b not equal to I has one less qubit. And hence, when we take this partial inner product, it would just give rise to a 2x2 complex matrix. And we properly normalize it by the trace. And now all we're doing is just taking the fidelity between these two one-qubit states. So first, this b not equal to I row b not equal to I is the unnormalized state. It's the taking row, and then what is it's essentially the probability of getting b not equal to I times the post-measurement state. And now we're just taking the product of them and taking the trace. And hence, this E of the omega is a number that's always between 0 and 1. And in a way, when it's very close to 1, it means that this one-qubit state is always matching with each other. And if they're not, then it will be much closer to 0. So E of omega is this number that's between 0 and 1 that kind of captures, roughly captures, or a bit captures how the one qubit post-measurement state matches with each other. We can also write down this formula in terms of as an operator. So here, this L psi, one can just think of pulling up all the parts corresponding to everything except for rho. So essentially wrapping the partial inner product b not equal to I around, and then massaging everything and grouping everything. Now we would obtain this observable L psi. So in a way, what this is essentially doing is we're just evaluating some observable that looks a little bit strange, and that corresponds to capturing this one qubit object onto rho. And this is a number that's between 0 and 1. And when it's very close to 1, it means that all the single qubit state are matching quite nicely. However, that doesn't really tell us whether the whole state is matching, because we're just kind of looking at single qubit one at a time. However, one can essentially try to understand what this observable corresponds to. So first, this observable has eigenvalues between 0 and 1. And there's always an eigenvector, psi, that corresponds to an eigenvalue of 1. And the reason is because if rho is exactly equal to psi, the target state psi, then every time when we do this single qubit when we post-select and kind of collapse onto this single qubit state, it would always be matching. And hence, this expectation value should always be 1. And as a result, there must be this eigenvector, psi, that corresponds to an eigenvalue of 1. However, the spectrum is a little bit more complicated. And basically, what one could show, or in a way, there's going to be a second largest eigenvalue that corresponds to 1 minus 1 over tau. And here, it's not yet clear what tau is, but I'm going to define that later. But what we're going to do now is to essentially look at the spectrum of this and try to think about what tau is. So in order to define tau, we have to talk about a concept called relaxation time, kind of basically similar to the mixing time. But what is the mixing time of? So here we have this target state psi. That's an unqubit target state. And we have also chosen some basis. So that's the z basis that we chose right now. But in general, we can choose any basis. So that's how we fix this basis. And now we consider the measurement distribution pi of b to be when we measure the target state psi in terms of this basis, then we will see some probability distribution that comes out of it. And we can think of that as the probability distribution over this Boolean hypercube. So now we wanted to consider some random walk on this n-bit Boolean hypercube. So what is this random walk? So first, let's say the walker is sitting at some bit string corresponding to bit string B, 0, 1, 0. And the random walk just proceeds as follows. At every step of the random walk, the walker will randomly choose one of its neighbor on the Boolean hypercube. So let's say it chooses to flip the second bit. So now it's connecting to 0, 0, 0. What it would do is that it would either choose to stay in the original place that it's been with a probability proportional to pi of b, which is the probability for that given bit string, or it might jump to that neighbor with probability proportional to pi of b prime. And that's the random walk. So every time, so initially it would start out at some random point. And then at every step, it will just go through this process, either taking a jump to a neighbor or stay there with a probability that's proportional to this measurement distribution pi of b. Then this number tau is actually the time it takes for the random walk to relax to the stationary distribution pi, so the measurement distribution. So if you run it for a long enough time, then in most cases, it would just converge to the stationary distribution pi, because it's essentially jumping based on pi of b. So for example, if pi of b, let's say we focus on this case that we talked about, the phase state case, the random phase state. In that case, the pi of b would just be the uniform distribution. And in that case, every time what it would do is it would either choose to stay where it was, or it would jump to one of its neighbor randomly. So it's essentially a lazy mixing, a lazy random walk with the uniform distribution as the stationary distribution. And for that case, the relaxation time tau is just linear in system size. It would be linear in tau, or linear in n. And what one can actually show is by looking at this crazy looking observable L psi properly, one can see that the spectrum actually is closely related to tau. Basically, the second largest eigenvalue would be given by 1 minus 1 over tau. And that's a very useful thing. And the reason is that with this structure, basically what one could show is, or one could essentially relate this object that was coming out from these strangely looking post-processing that we were doing to analyze the data that we talked about, to relate it back to this global object. So if we see that this E of omega is close to 1, it's greater than or equal to 1 minus epsilon, then because of the spectrum and the structure, so it has the top eigenvector of psi with the eigenvalue of 1, and then the second largest one always is given by 1 minus 1 over tau, then one can actually show that the global fidelity, psi rho psi, would be greater than or equal to 1 minus tau epsilon. So if this E of omega is close to 1, it also implies that the fidelity will be close to 1. And on the other hand, one could also prove that if the global fidelity is close to 1, then this E of omega, which essentially just look at single qubit one at a time, would also be close to 1. So basically, by writing out this analytical form and by massaging it, one can actually relate how close looking at this number, E of omega, connects to this random walk time. And in particular, like the case that I talked about, let's say this phase state case, because it corresponds to a random walk that will converge to uniform, and it will converge very quickly. There will be rapid mixing that happens here. So it only takes a roughly linear time in order to converge, and hence tau is just linear. And what that means is if one sees that E of omega is close to 1, then one would know that the fidelity would also be close to 1. So essentially what this allows us to do is that it allows us to perform just single qubit measurement, and from the collection of data, going through this post-processing, one will be able to essentially test fidelity. And it essentially leads to the following theorem. It says that for any n-qubit state psi with a relaxation time of tau, we can certify whether a state rho, arbitrary lap state, is close to psi or not using just order tau single qubit measurements. So the faster it's mixing, then the faster we can certify it.
So you use as an example that like 1/2 with the arbitrary phases. I guess it's just not clear to me that would work for arbitrary amplitudes as well. Does it?
There's a next theorem that I'm going to showcase.
Okay.
Yes, but that's a great question. So it's not entirely clear, and it really depends on how fast things are mixing. But at least when things are mixing quickly, then this theorem tells us that one can certify efficiently using single qubit measurement, and this includes this case where it's just a arbitrary phase state. And note that here, unlike in XDB, the certification procedure applies to any state that we wanted to certify. So any state in the lab. The theorem allows us to tell if it's actually close, or whenever there's some adversarial noise, like dephasing or some other noise, one will be able to efficiently test that and falsify it. And so now the question is, for a given target state, what is the mixing time? What is the relaxation time for the random walk?
Hi. So on the previous slide, when you had the two implications, and the second implication no longer involves the relaxation time tau.
Yes.
Could you explain to me how that goes away?
Yeah, so basically one way to see the second one, so the second one doesn't involve anything. That's just true in general. And the reason is because E of omega is essentially just testing like a single qubit fidelity. So if the global fidelity is good, one can basically from there just immediately derive that all the single qubit fidelity that we measure would also be good. So that's one way to think about it. Whereas, so it's kind of like if things are good globally, then of course locally things are also good. But the non-trivial thing is really the first part, where we only get things that are good locally, but somehow it's implying things about the global nature of things.
Yeah. Like, how do you connect the relaxation time with the spectrum of the psi? Like, I don't get it intuitively how.
Yeah, so that would require a bit more working, but essentially one needs to write out the definition of L psi according to this form that was written here. But basically one can, the way that things are being connected is as follows. So every time I wrote this B not equal to I, one should think of it really as like an edge on the Boolean hypercube, because it's just saying, okay, I specify n-1 bits, and only one bit is left unchanged. And if I put in 0 versus 1, it essentially corresponds to two different vertices that is connected on the Boolean hypercube. So B not equal to I should be thought of as it's specifying a given edge. And which edge it is also depends on I. So which qubit or which bit we're not fixing would essentially be specified by both I and B not equal to I. And the interesting thing is that this L psi that's written here, by properly massaging it, actually corresponds to the same metrics that comes up when we do random walking. So here I talked about a random walk, essentially a random walk on this Boolean hypercube, where I can jump and move around so far, like this. And basically in random walk literature, the relaxation time corresponds to essentially like the second eigenvalue of the corresponding jump, like a jump operator, or this the Walker matrix. And basically that Walker matrix, if one write it out properly, is closely connected to this L matrix. And that's why the second largest eigenvalue for this L observable actually is closely related to the relaxation time of this random walk that we talked about. So hope that provides some intuition. It wasn't, yeah, it wouldn't be too hard. Like just writing things out properly, then it would actually match up.
Thank you.
Hi.
Yeah.
Hi. It seems to me that LSI can actually be written down as a stochastic transition matrix.
Yes, yes,
and
yes.
then the spectral gap of transition matrix is actually inversely related to the mixing time,
Yes.
like in a normal MCMC as well, which is exactly what the result is over here because the spectral gap is 1 by tau.
Yes.
So is that the correct intuition?
Yes,
for
that's
it?
right. That's right. Basically, writing it out would see that that's the stochastic transition matrix. So yeah, so from the theorem, it essentially shows that there's a tight connection between rapid mixing, which I would guess in the morning tutorial, they also talked about it. It's now showing up again, to how fast we can efficiently certify things. But as raised by one of the previous questions, it's not entirely clear that this should be the case. So here's a second theorem. Basically, one can show that for almost all n-qubit state, it will be rapid mixing. So given any except for an exponentially small fraction of state psi, one can show that if one look at this random walk on that Boolean hypercube, it will be rapid mixing with mixing time, relaxation time, that's upper bounded by n squared. And hence, one immediately obtained this theorem, which states that for almost all n-qubit state psi, generic ones, we can certify whether the lab state roll is close to our target state using only order n squared single qubit measurements. And that answers one of the questions that I posed earlier. So note that here, order n squared number of single qubit measurement is already enough, even when psi has exponential amount of circuit complexity. And note that here, we're only really doing just single qubit measurement and looking at things in a kind of a single qubit by single qubit fashion. However, somehow, the single qubit measurement is sufficient for us to test all kinds of, or almost all kinds of, n-qubit entanglement.
Hey, Robert.
Yeah.
Thanks for the talk so far. How many copies of rho do you need?
Order n squared.
Oh, so each measurement is going to consume a copy of the state.
Yes, that's right, that's right.
Okay, thank you.
So the measurement here is really the protocol that I just described earlier, where we randomly choose one qubit, measure that in the random XYZ basis, and everything else just measure in the standard Z basis.
Okay,
So that's
thank
the
you.
protocol. Yeah.
I have another question, please. So does this apply to any basis? Like you choose a basis and it will be...
Yes.
Yeah, all right.
Yes.
Hi. Yeah, this is a really cool example, and given how simple this protocol is, and yeah, I guess how neatly everything works out, is there scope to try and extend it for all n-qubit states? Like, can it?
Yeah, actually, there's going to be a question later that poses exactly that. So, so far our result only holds for almost any n-qubit state, but right now, actually, that remains an open question. Like, could we strengthen the whole thing just to say that for all n-qubit state psi, we can always certify whether an arbitrary lab state is close to psi or not using a polynomial number of single qubit measurement. That would be a fascinating result. I don't know the answer to it. I don't know, like, yeah, I think it could go both ways. In a way, I would be extremely surprised if that's true. But to be honest, I'm also already surprised by this theorem. So my intuition is just wrong. But then, but then one could also say maybe the answer should be no. But then, how do we prove that there are just no protocols involving single qubit measurement that can do it? It's also not clear that way. So it could go both ways. That's a good question.
Can we say anything about the worst case gap? Like, is there an upper bound on the number of copies you can do in the worst case?
Right. So with this specific protocol, so the measurement protocol that I described is just like the simplest version. One can enhance it using some of the ideas that you guys have also come up with. For example, instead of just choosing one fixed basis, like all Z bases, one could also play with choosing a few random bases or just keep changing bases every time and so on. I don't really know what would happen in that case. If one focuses on the simplest case, that is all Z bases, we only measure in all Z bases and look at this, there are a lot of simple situations that one can construct where the mixing time will be very long, right? Like for example, if psi is just supported on the two ends of the Boolean hypercube, then in that case the mixing time could be very long because it's like a bell. But then one such example is GHG state. But as we have also seen earlier, for GHG state, one could also just certify them efficiently using single qubit measurement by just testing stabilizers. So right now I would say it's unclear. But for a given fixed basis, there are counterexamples like GHG state.
Thanks. I have a question as well.
Yeah.
So how does noise affect this result? Like if you have measurement noise or the repeated preparation of the state incurs some noise, do things like explode and suddenly things become exponentially costly, or is it super robust and it's still
right?
So
it would depend on how we attribute noise, because in a way one could say that, let's say there's a process for creating state rho, and then there's this middle process right before measurement where a noise happens, and then I measure. So now how should I attribute the noise to? Should I attribute the noise to the state? So I could do that. If I do that, then in a way it just says my state is slightly changed. And so now when I'm doing certification, I'm doing certification on a state that also includes this final part. And then in that case, all the theorem works because the certification procedure, the guarantees holds for any rho. So this final measurement, if I attribute it to part of this being the state, part of the lab state, then yes. But then one could also say, what if I attribute that to part of the measurement? But then in that case, one would have to first apply some noise learning technique in order to learn the noise, and then try to do some kind of calibrations away from that. So one could also do that, which I think it should be possible. Like the procedure here that I talked about is extremely simple, so it's pretty robust to all of them.
Thank you.
No problem.
Oh, so many. Go here first.
Hi, could you give us the intuition about why there's a huge difference in the number of measurements compared to solely use the classical shadow tomography based on the random Pauli measurement, as you say, is exponential number of measurements?
Yeah, so that's a great question too. So to be honest, I think the answer is not with respect to measurement procedure. So here, the measurement procedure is, in a way, much simpler than randomized Pauli measurement. So in randomized Pauli measurement, I mean, it's already simple, but we need to change bases every time for each qubit. And yet, somehow, I was saying earlier that this would require an exponential number of measurement, whereas here, we're measuring almost everything in Z basis and only a single qubit in a random basis, and suddenly it becomes an unsquared number of measurements. So I think probably the full story is that even when we do these randomized Pauli measurement, it should also just be unsquared single qubit measurement, but the post-processing should be different, or the way we analyze things should be different. So it's more like combining the post-processing that people often do using classical shadow formalism, as well as the analysis that come with it. Using that whole procedure to do state certification would require an exponential number of measurement. But it could be that maybe the same procedure or like the same post-processing still works. It's only, probably that would also have to change, because the way people do state certification using randomized measurement, people are multiplying things by some exponential numbers. And that's going to cause statistical fluctuation to be extremely large, and hence the number of measurement would also be extremely high. So yeah, so I think by changing the post-processing as well as the analysis, suddenly it speeds up exponentially. However, I don't think the measurement procedure itself is the problem. Like, one should be able to fix the same measurement procedure, but just do a different post-processing and do a different analysis. One should also get this result.
Here in the middle.
Yep.
So is this statement also true if you take almost all n-qubit mixed states?
So I would say it will not be true. Let's say if we take the target state to be the maximally mixed state, the infinite temperature state, then the exercise that we went through earlier already shows that it's hard to certify infinite temperature Gibbs state. So yeah, so then one could also try to play with it. So instead of infinite temperature Gibbs state, let's say I consider a highly mixed state, and that's our target state. And then I consider almost all in the sense that I change the basis around. That would still be hard because of the hardness of testing entropy and so on. So hope that clarifies it.
Hello. Yeah. Is there a quantification on almost all n-qubit states? Like, what are we talking about? Like almost everywhere, for instance, or?
Yeah. So here, more formally, one could think of it this way. So for another way to say it is consider the entire space of pure states psi. Then for all except an exponentially small fraction of them, one would be able to certify it. So that's, yeah.
Coming back to the previous question, I think if you say for almost all n-qubit states with rank poly n, then it should be true,
yes,
right?
Then I think if it's...
So if you have a very good rank promise, you
yes.
still should get results.
Yes, that's true. That's true. There should be, whether how efficient we can test things should definitely with having a rank comes into play, or maybe how mixed the thing is and so on.
So you just said that it depends on the processing that you do and not so much on the measurement protocol. So can we expect that there is some other processing that reduces the amount of measurements or the number of copies, or is this like a bound that you have?
No, we don't have any, or I don't have any matching lower bound that says order n squared is the best. So it could be that this can be significantly improved. That's also a possibility.
Sorry, just to clarify, so can you give an example of a pure state that's like extremely difficult? Because you said there are an exponentially small number of states. That's very difficult, right? What are that kind of states and?
Yeah, that's a good question. So I'm just saying that the theorem guarantees that for all except for an exponentially small fraction of states, it would be easy, but it doesn't say for that exponentially small fraction, it's going to be hard. So there's no.
Okay, gotcha.
And that's related to one of the questions asked earlier, that is it possible that we can just strengthen it so that it just holds for all n-qubit state? And that's still an open question. So yeah, and so let's continue. So now after we have seen, we have go through these exercises to think more about state certification, I guess an immediate question that one would ask is, what can we use state certification for? So what are some interesting applications that comes out of it? So the first one, which is related to one of the motivations that I said, is that certification allows us to test and to benchmark quantum devices. That's also the application that people have in mind when people are playing with XEB and try to better understand cross-entropy benchmarking. So what one could do here is say compare between using XEB to do benchmarking versus using this new kind of idea, this E of omega method to do benchmarking. So because we're essentially calculating, utilizing this classical shadow on single qubits to calculate overlaps, so I'm going to refer to that as shadow overlap. So here's a plot. So if we consider 4-qubit hard random state subject to white noise, which is a case where XEB is known to work, then we can see that XEB is doing pretty well. So as the white noise amount increases, XEB is decreasing and matching the true fidelity. And here, the same also applies to shadow overlap. And now we've also gone through this exercise where we look at what happens if there's dephasing noise. So if the noise affecting the system is dephasing, where it just dampens away all the off-diagonal parts, then XCB is not going to see that. So as the noise increases, XCB still maintains a perfect score, as we have gone through in one of the questions earlier. On the other hand, we can see that shadow overlap would decrease. So in this case, one can utilize shadow overlap to accurately perform certification and to benchmark quantum devices, whereas using XCB, one would have a completely false conclusion. So here's another example, but subject to coherent noise. So suppose that the state that we prepare in the lab is still pure, but it's subject to some coherent noise, so it's some other target state. As the amount of coherent noise increases, we see that the deviation of XCB from the true fidelity increases. Whereas shallow overlap, there's still a deviation because there's no guarantee that shallow overlap must track fidelity exactly, but we can see that it better captures this noise. One could also play with some other randomly structured state. So here we consider having some product state and apply some, here we look at having some product state and apply some random phase operator to the state. So in terms of white noise, which is a case where XCB is known to work, we can see that it is indeed working, even though the variance is a bit higher. On the other hand, as we have seen, when there's dephasing noise, then XCB would completely confuse itself and thought it's perfect, even though there is a strong amount of noise in the system. And now if we have coherent noise on this structure state, then suddenly XCB could, in principle, behave unexpectedly. And so in this case, which is kind of strangely, as the coherent noise increases, XCB scores start to blow up and then go beyond 1. On the other hand, utilizing this method that we've been looking at, it can more accurately track it since it's a rigorous protocol. We can also look at similar situation, but for slightly bigger system. So this is white noise, this is dephasing noise, and this is coherent noise. We can even scale it up to, let's say, 20 qubit. Then again, in 20 qubit system, in terms of dephasing noise, XCB is still doing poorly. And in coherent noise, it has some unexpected behavior. So by designing efficient state certification protocol, we can do benchmarking. That's like a very straightforward application of state certification. But one can also think about some other more complicated tasks, such as a proper learning task. How can we use certification for doing learning? So suppose that we have a given parameterized family of states. Maybe it's a neural network, maybe it's some other representation, but it's parameterized by a high-dimensional vector x. And what we would like to do is we would like to learn psi of x star that is closest to the lab state rho by performing just single qubit measurement. So how can we utilize state certification to do learning task? So feel free to think a bit about it and raise your hand if you have any questions or thoughts about this question. Yeah, go ahead.
This is basically VQE. Okay, that's it. So yeah, you do a classical optimization loop on the X space, and then do these like efficient measurements for each experiment, and then try to decrease or increase fidelity, basically.
I see. So you're thinking of it really as like a VQE strategy where you collect all these data, and then from there calculate these shadow overlap that I called, and then from there we tune the parameter and collect again and try to go through this. Yeah, that's a good idea. But could we make it even more efficient?
do we have any kind of promise that there is a state in the family that is close to P within some range, or is it possible that the closest one might be very different from rho?
Yeah, the closest one could be kind of different from rho, but so I don't think we need any. But maybe that's for simplicity. Assume there is one that's pretty close. There is one that's very close.
I mean, the procedure we developed previously is kind of, the procedure we developed previously is kind of like a fidelity estimate in some ways. And that fidelity will be a loss function. And then we can train a neural network. But that's like not a mathematically correct solution, but that's just a heuristic.
Yeah, that's indeed. And maybe one thing I would like to emphasize is that the procedure that we talked about, the measurement procedure is extremely simple. And in order to test fidelity between the state role, or to certify things between state role from any of these target state psi, we can just keep using exactly the same data set. So all we have to do is to just collect this data set, and now one can utilize standard concentration inequalities like Hofstad's and so on to immediately prove that from the same set of data set, we can predict the fidelity for an exponential number of target state. And all of that is going to be accurate. And hence, from that result, one can immediately show that if I have a parameterized family, let's say there's like a polynomial number of parameters, then I would only need to perform, and let's say this family is nice, like it falls into this almost all kind of class, then one can show that just by performing a polynomial number of single qubit measurements, we will be able to collect all these data that allows us to learn the one that's closest to rho. So information theoretically, that's possible. But then, of course, there's also a question about optimization. So this parameterized family can be pretty complicated. And if that's the case, then we could run into some computational issue. But in many cases, this parameterized family could look very nice. And now in that case, we can just use that measurement data set and then do like a training of neural network or training of tensor network in order to figure out this. So through this question, I hope it clarifies the relation between certification and learning. In a way, even though certification sounds like a very specific protocol, I'm just trying to test something that's very easy. In often cases, when we make advancements in designing better state certification protocols, it can immediately lead to advancements in state learning. So here's another question. But I think this one is slightly much easier. So if you're given some trained neural network model, let's say some AI person that uses its fabulous transformers to try to represent some quantum state. There have been a lot of research in this direction as well. To try to represent and try to learn a representation of a given quantum state rho. How can we certify it? So how can we check that psi is close to rho? So psi here corresponds to the representation learned by a heuristic AI model. And in many cases, this neural network might hallucinate, it might get stuck, but sometimes it can really learn hidden patterns so that from a small amount of data, it will already be able to figure out a good representation of the underlying state in the quantum system. How can we efficiently certify that the neural network is actually correct? And of course, the answer is we just run the procedure that we developed so far. So that's another application for using state certification to certify heuristic AI models, which might be able to use much fewer amount of samples than we would originally expect. However, previously, a lot of times when people use it, there's this concern that neural network might just be producing incorrect things, might just be hallucinating. However, with these certification tools at hand, we can check that. And now, after we have checked it, we know that the neural network has learned well and is correct. And now all the results that comes out of the neural network, we can be sure that they would also be certified.
Sorry, I'm slightly confused by this because you said in the slides, you said neural network representation of psi, which means that directly that literally means that we don't really have the knowledge of psi inside knowledge of psi stored in neural network. And the process of the overlapping shadow, the shadow overlap you're doing is like you are asking some properties of psi, and you assume that the properties of must be self-consistent, right? Like, what if the neural network is not even consistent when it's when you ask different properties of a psi, and then that will cause issues, right? Unless you have to first like turn that neural network representation into an actual correct representation of psi.
Yeah, so that's a great question. In a way, the setting is non-trivial because we don't know, in a way, like, let's say I'm the person that tried to do the certification. I don't even know what psi is. Because here, the psi is represented using a neural network. So here, when I say a neural network representation, I'm using this neural quantum state representation that people in condensed matter has been studying, which is it's a neural network that takes in a bit string x, and it spits out the probability amplitude x psi. So it has this specific form. And in a way, that specific form already constrains what the neural network representation looks like. So yes, so I don't know the neural network. In a way, the neural network is like a black box to me. And there's another black box, which is the quantum system that was created in the lab. So in this certification task, we are trying to certify two black boxes and to say that they're actually close. One is the one in the physical world, and one is this kind of digital one in a neural network. And however, if one assumes this representation, that is the neural network will spit out x psi, which is a complex number, then actually if one go back to the certification procedure that we were talking about, all we need to do to run that certification procedure is that every time when we get a bit string, we will be able to query x psi, which is allowed and given by this neural quantum state representation. And hence, in this case, we will be able to run this procedure accurately. But of course, you could also say maybe the neural network, when you query it the same bit string twice, then it will start spitting out completely different things. And that's the second, that's a separate issue. Here I'm assuming that every time when you ask it with the right bit string or the same bit string, it will spit out the same result. Yes. Let's say it spits out a normalized number. Yes. No problem.
Yeah, I think in addition to that, you also need this assumption that the rank is bounded of one of the states. And since you cannot guarantee that the lab state has bounded rank, maybe that's an assumption on the neural network state.
Yeah, so of course, people have also been studying this, but oftentimes in this neural network representation, people consider it to be pure state. So the rank is already just one. And
can that be guaranteed?
It depends on the representation, but it could be guaranteed. Like they can design your network so that this is always guaranteed and it's always normalized. So that can be guaranteed. But of course, people have also been studying different forms. So it's like a mixed state, neural quantum state, where it could be high rank. In that case, it would not be guaranteed. Yes.
Thanks.
So once we have this neural network representation, what do you think a practical use of this could be?
Yeah, so there are many powerful things that the community, the neural network quantum state community has established. Basically, one can think of this neural network as providing so first we can, by measuring state role, we can get sample data. And essentially this neural network quantum state representation is a query model. So if you're familiar with this literature on dequantization, it often assumes its ability to both obtain sample access to a state as well as query access to a state. If one get both, then one can do a lot of crazy things. So here, after certifying this neural network, you essentially get a query access to the unknown state you have. And then you can estimate many things by performing just single qubit measurement. So one thing that immediately comes to my mind is, for example, if you wanted to calculate some expectation value of some complicated sparse observable onto your state role, but you're only given the ability to perform single qubit measurement, then it can be very challenging to measure such a sparse observable O. But now after you have this representation, you can essentially combine with it, like you can do some querying and some sampling, like you take samples from measuring state role in the computational basis, and then also query the neural network. Then together you can estimate any sparse observables efficiently. So that's one example. You can also estimate things like, essentially you can use this neural network to simulate multi-copy measurements by just performing single qubit measurement on state role. So having this representation really is a very powerful thing.
I see. So apart from the neural network representation, do you think we can have some other approximate representation?
Yes, yes. Actually, what I just said also translates to other representation. As long as you have some representation, it could be a tensor network, it could be some other new ones that there's no name. As long as you can have this ability of feeding in some bit string and getting out some probability amplitude, then you can do all that I said.
Thank you. So when you say efficiently, do you mean that you need poly-n copies of row, but do you also mean in number of queries to the neural network?
Yes, so it's efficient in all of that. So it's efficient in terms of number of queries to a neural network, the number of copies and the measurement data, and also the computational time.
I see.
So all of that.
Okay, thanks.
But yeah, but there is an interesting thing. So like in our community, there have been these dequantization results which were very powerful in dequantizing quantum machine learning algorithm. But somehow separately in the neural quantum state literature, they also have been developing these sample and query access models that allows one to efficiently extract properties out of quantum systems. However, previously the main issue is really that after you train this neural network, it's just a heuristic model, so you cannot really make sure that it's correct. And a lot of times, or in many cases, it could hallucinate. But now with the ability to certify it, and now you can do all of this with rigorous guarantee. So that gives rise to these other application, which is by having state certification, it allows us to certify and also to train different classical representation of quantum state, including these ML models, such as neural quantum state. So due to the time constraint, I'll be a little bit faster here, but oftentimes what people consider is the standard model of like standard neural quantum state model, where you just put in some bit string and the neural network spit out things. But one can also play with some more advanced version, which we considered, which we called the relative neural quantum state. We just put in 2 bit strings and it spits out the ratio of the probability amplitude. This still represents the same wave function because by querying this neural network multiple times, it allows one to just multiply the ratio together, and now you can get the probability amplitude. And the reason that we consider this is because it's using this relative neural quantum state is easier to train using the data that we obtain from the procedure that I talked about earlier. So here's just some example where we try to learn a class of 120 qubit states with extremely high circuit complexity. So the subsystem purity decays exponentially if we look at if we look at it. So initially, when we randomly initialize the neural network representation of the quantum state, it was an unentangled state. But now what we can then do is we can then utilize this data that we talked about to train it, to learn it, and also to certify it by calculating this shadow overlap. And the result is shown to the right. So here the x-axis corresponds to the number of steps that the neural network is training. And the blue one corresponds to some loss function that we designed. And so after some time, the loss functions start to decrease and seems to be saturating. However, at this point, we actually don't know for sure that the neural network has succeeded. It could be that it got stuck in some weird local minima, and maybe it's hallucinating things. So at that point, but just by looking at the loss function, we cannot tell whether the neural network actually has learned the quantum state in the lab or not. However, by also estimating this shadow overlap or running this certification protocol that we talked about, we will be able to test that efficiently. And after we have certified it, now we can be sure that when we use the neural quantum state to make predictions, it will be very accurate. So for example, we can use the neural quantum state. Note that when we train it and also certify it, we only use single qubit measurement. But from only single qubit measurement, along with this learned representation, we can estimate all kinds of observables, including things that are highly nonlinear, and that requires multiple copies. So we don't need multi-copy measurements in order to create things that, in general, will require multi-copy measurements. But here, by just training this neural quantum state, we will be able to predict that accurately with rigorous guarantee. So here is some prediction from the neural quantum state, and we can see that it tracks the ground truths very accurately. So that's just another application of using state certification. Here's another one, but before diving into that, let me show a question. So one can ask the following. So even though these shadow overlap quantity that we talked about has this nice implication that if it's close to 1, then the true fidelity would also be close to 1, and if it's far from 1, then the true fidelity would be far from 1. One could also ask the question, how do they actually differ? And let's say we focus on these collection of states, then how do they differ in terms of their values? So the analytical formula is given below. For some of you that are quick, hopefully you can just immediately calculate it and figure out the answer. But it's okay if it's too complicated. Yeah.
I'd say that anytime the two states are close in Hamming distance, the shadow overlap will be pretty high, but the fidelity can be low. It can be even 0 if you want. So it's a good property for learning, like the landscape is smoother.
Yeah, that's a very good observation. So basically, one of the bad side about fidelity is that it has a very clear barren plateau feature. So it has a sink in the middle when you're really close, but then when you're just slightly far away, you suddenly becomes bad. On the other hand, because this shadow overlap is looking at things that are much more single qubit, so if you calculate all these examples, you will see that it has a much more Hamming distance flavor. And hence, by utilizing these new metric, one can obtain a better landscape. And so another application of state certification protocol is that we can use it to optimize circuits. Suppose we wanted to prepare some target state psi, and now we have all kinds of knobs and gates that we can tune in the actual lab. We can try to optimize the circuit to maximize the certifier in order to prepare the desired target state. So here's just an example. So suppose we wanted to create some n-qubit MPS using Hadamard, CZ, and T gates. So if you run the correct sequence, so the x-axis here corresponds to running the correct gate sequence to generate the state, then we see that when we, in small system size, both fidelity and this new metric that we have been looking at both works pretty well. On the other hand, when we look at 50 qubit, we see that fidelity has this barren plateau feature, so it's not changing. The metric is just staying at 0 for a long time until at the very end when we get very close. On the other hand, when we utilize this new metric that we have been playing with, and we see that it has a much more Hamming distance flavor and just keep growing up. And hence, when we just apply and try to train the circuit, train the state preparation circuit, using some Monte Carlo optimization methods to prepare it, it will work much better. So with fidelity, it would just be random walking, but with this shadow overlap, or this metric that we've been looking at, it will be much clearer. So yeah, so I hope that gives a bit of flavor for how one can use certification protocol. Oh, there's
Hi, going back to the last slide.
Yes.
Can this be used to just like synthesize circuits in general and not their the particular output state? Or is there some kind of barrier there?
Yeah, so right now we've been looking at is this new certification, or try to understand new certification protocol for certifying states. But of course, one could also try to design new certification protocol for certifying unitaries and channels, etc. And we would have to develop that in order to apply it to unitaries.
I was just curious, could you compare this method with if you use reinforcement learning type techniques to optimize a circuit?
Yeah, so here we're just, I'm just using, the purpose here is just to demonstrate that by doing single qubit measurement, we can create some metrics such that it will be able to certify things and to train things. Here I'm just using almost a simple vanilla Monte Carlo optimization. So if one replaces that with a more advanced RL technique, I would expect it to work even better. Yeah. I think so. Here it's really just a simple Monte Carlo. Yeah.
I have another question. So, I mean, it's often like in physics, you have this intuition that, you know, like a more physical distance between, let's say you want to prepare a ground state, the more physical distance to the state is maybe energy, because, you know, overlap is like you go to excited state, suddenly it's zero, right?
Yes.
So is it feasible that maybe, I don't know, have you thought about this, that if, let's say, for low energy states and like local models or something like this, the shadow overlap will be close to 1, the overlap, of course, can be 0, like something, ideas along those lines?
Yeah, in a way, one way to think about this is really like, if we go back to very early on, like this L operator, you can think of this L operator as kind of like some form of Hamiltonian. So in a way, this shadow overlap is kind of like, given a quantum state I wanted to certify, create some type of observable Hamiltonian energy-ish that is much more local to that still captures this. So. Yeah, it could be. I don't really know the relationship between Hamiltonians and shadow overlap, but I think that's a good question to explore. But yeah, so here's a final question, basically the one that people have also asked. So we've seen that one could certify almost all state, but yet it still leaves open this question: can we efficiently certify any state with few single qubit measurement? Could it be that single qubit measurement are just somehow surprisingly powerful, that just by doing so we can actually see all type of long range entanglement that's in the state? We've seen that it seems like it's almost true, but could it be that this is actually always true? So that's a question for all of you. I don't know the answer. I tried thinking about it, but didn't solve it. So yeah. So to conclude, as we have seen, to accelerate and to automate quantum science, it's critical to understand how to design better algorithms to learn the quantum universe. However, we've also seen empirically and in many cases that the most powerful learners, humans or machines, have these emergent capabilities that are inherently heuristics, which are by definition unpredictable by first principle, and hence we shouldn't be able to write down a fully rigorous end-to-end learning theorem that talks about these much more powerful learners. However, it raises this additional, this alternative question. So instead of designing this end-to-end learning algorithm that works in all cases, what if we just focus on designing new rigorous certification or verification protocols that can harness and validate these empirically powerful emergent capabilities? So in terms of learning, I think some of the broader question is, in the future, how can we design future quantum AI to learn model, extract properties about our world? And in terms of certification, the overarching question is, when a future quantum AI can learn models and extract properties, make predictions better than all of us, how can we make sure and harness its power? More specifically, one can ask all kinds of questions. We can ask, when some future quantum AI says it founds a new low-depth quantum circuit for simulating electronic structure, how can we certify it? How can we harness it in a rigorous fashion? We can also ask the same question about algorithm. If we have some heuristic quantum AI model that can design new quantum algorithm with or that claims that it can design new quantum algorithm with genuine quantum advantage, how can we certify and harness it? We can also ask about state of matter. Say a future quantum AI or some experimentalist claims that it has discovered a new state of matter. How can we certify it rigorously and harness it? And the same for sensing. When a future quantum AI says it it has sensed some Axion dark matter, how to certify and harness it rigorously. So yeah, so together, this is just the long-term goal for quantum learning and certification. We wanted to continue to develop our understanding of learning to accelerate and automate science. But at the same time, if we wanted to harness some of these more superhuman or like emergent capabilities, how can we design rigorous and new certification protocols to validate them? So thank you so much for listening.
Thank you so much, Robert. I think in the interest of time, I would say we can ask questions offline. There is a session at 6 p.m. On peer review by the physical review family. And tomorrow we have 2 exciting tutorials, one on QEC, another on quantum crypto. So let's thank both the speakers today and see you at 6 p.m. and tomorrow.